Hello, everyone. I'm David Lunseter from DigiKey Electronics, and welcome to today's webinar, Harnessing the Power of GaN for Motor Drives. Before we get started, I would like to go over a few housekeeping items for today's event. You will have the opportunity to submit text questions to Alex by typing your questions into the Q&A feature at the bottom of the screen. You may send in your questions at any time. We will collect these and address them during the Q&A session at the end of today's presentation. At the conclusion of the webinar, we will be selecting one participant at random to receive a copy of the 3rd edition book, GaN Transistors for Efficient Power Conversion. If you're the lucky winner, you will be contacted in the next few days for your shipping information. Now, I would like to introduce our panel today. We have Marco Palma, Senior Field Applications Engineering Manager at EPC, located in Turin, Italy. Marco has over 20 years of field experience within the semiconductor industry, working with customers to define innovative solutions to meet the unique challenges of each customer design. Most recently at EPC, in addition to customer support, he's been involved with application support using the GaN power stage in motor drive designs. Welcome, Marco.
Hi, everybody. Hi, everybody.
And our speaker today is Alex Lido. Alex is CEO and co-founder of Efficient Power Conversion. As co-inventor of the HEXFET power MOSFET, Alex holds many patents in power semiconductor technology and has authored numerous publications on related subjects, including co-authoring the first textbook on GaN Transistors for Efficient Power Conversion. Alex, thank you for joining us today.
Thank you, David. Thanks to all our friends at DigiKey, and thanks to everybody for attending. In this webinar, we're going to show how GaN-based solutions are improving motor drives, and they're enabling smaller, lighter, more precise systems that make less noise. We'll review some key applications using these systems, including e-mobility, cobots and robots, DC servo drives, drones, and automotive. First, we'll explain the value of eGaN devices for 48-volt motor drives, and then we'll review key applications. Next, we'll look at EPC's product portfolio for motor drives, and lastly, we'll get a look at our field application engineering lab in Italy, where Marco will give us a demonstration of a GaN-based motor drive. Brushless DC motors are a class of permanent magnet motors that operate at voltages and currents well aligned to eGaN FET capability. They're popular because their high torque and power density gives them a small size. They can operate over a wide speed range, very high efficiency, and they're brushless, so there's much lower EMI generation. And brushless DC motors are being used in an increasing number of applications, such as robots for precision control, and in places like medical, manufacturing, warehouse robots, drones that require very lightweight and efficient solutions, and e-bike and e-scooter traction drives that need to be small and low cost. And in this webinar, we'll show a simple, compact, lightweight approach to a motor drive using our GaN integrated circuits. So let's look at the many applications for motor drives and discuss where gallium nitride fits and where it does not. And so what you're looking at here is basically a view of the universe of motor drives. On the vertical axis, you have the voltage of the drive, the input voltage, and on the horizontal axis, you have the current required by that application. And EPC's eGaN devices target applications where the input voltage is between 24 and 150 volts, and the sweet spot's really right at 48 volts. Key applications, as we've said, are brushless DC motors, or sometimes called BLDC for short. And typical applications are servo drives, e-bikes and e-scooters, collaborative and low voltage robots. By the way, collaborative robots are now called cobots, and medical robots, industrial drones, and automotive motors. In these applications, the motor drive is integrated to the motor, and miniaturization and lightweight is a key differentiator for eGaN devices. And finally, higher system efficiency is very important for longer battery life. And now let's look at where GaN is not necessarily a good fit. Brushed motors, and they're disappearing, so that's less of a problem. Most are driven with a side chopper that doesn't need speed control, and therefore these are not targets for GaN. As for stepper motors, it's typical for small appliances. This is really the domain of lower power MOSFETs. And for industrial robots and appliances, let's see, industrial robots and appliances, there we go. These generally are higher voltage and higher power. So this is really where high voltage IGBTs come into play. So now you have an idea of what portion of the motor drive market gallium nitride is best suited for. These are the applications where GaN adds the most value. So GaN FETs switch faster and have zero reverse recovery compared to MOSFETs. And that allows them to operate at higher frequency efficiently and reduce dead times to dead times that are much, much lower than you can achieve with MOSFETs or any other technology. So this opens up the possibility of higher switching frequency motor drives where 20 kilohertz to 60 kilohertz have traditionally been used. Additional benefits of operating at higher switching frequency include lower distortion of the applied voltage waveforms that allows higher speed while keeping acoustic noise low, lower ripple current, which reduces AC magnetic losses and thus gives you a higher efficiency motor and lower operating temperatures, reduced torque ripple, and that reduces the mechanical vibration that's not desired in applications such as servo motor, strength amplifiers, strength amplifiers like electric power steering, and also very fine adjustable motors like you might have in medical applications. Lower filtering requirement, and this reduces filter cost. It also reduces weight and size of the inverter. Electrolytic capacitors actually might eventually be replaced with ceramic capacitors, which greatly improves reliability and reduces size. And finally, this supports a newer class of low inductance motors, such as the slotless motors. So even though eGaN devices are very, very small, thermal efficiency is not really a concern because these devices have excellent thermal properties. On the left, on the vertical axis, you have the thermal resistance from the device junction to the board, and on the horizontal axis, you have the area of the device. The red dots are MOSFETs, the blue dots are eGaN devices. You can see the thermal resistance of an eGaN device is pretty similar to a MOSFET for the same die size. But if you look on the right, where you have the thermal resistance from the junction to the case, which is the outside world other than to the PC board, you'll see a huge difference. Again, the red dots are MOSFETs. These, in this case, the best MOSFETs you can find. These are direct FETs and blade FETs. And the blue are the eGaN FETs, chip scale package. And there's a 6x difference to the best in class MOSFETs. So even though these devices are smaller, they are much more thermally efficient. And just to bring that point home, here's an example. And the example shows a 4 square millimeter device, tiny, tiny device, and it can dissipate 6 watts with a temperature rise of only 24 degrees, or that's 4 degrees C per watt. By the way, we have a lot of additional information on thermal management that can be found on the EPC website, and it includes a complete seminar on thermal designs. But for motor drives, size and cost dominate, and efficiency is dominated by the motor. Therefore, a key objective of many applications is to drive the most current in as small a volume as possible. In many cases, you want to move that motor drive right into the motor housing. So you've got to be as tiny as possible and as thermally efficient as possible. And this is much more efficient than you can get with any packaged MOSFET. Now let's look at some key applications where eGaN FETs and ICs are making inroads. The major value of eGaN devices, we said, for cobots and low voltage robots is small size and low weight. Additionally, low switching losses enable an increase in the switching frequency, and that gives you higher precision. Well, high voltage industrial robots are usually based on AC drives that have a 38-volt three-phase input. A low voltage operation for these applications, cobots, robots, is preferred because there are humans nearby in the range of operation. So you really need more care, more fine motion, but also lower voltages. So collaborative robots or cobots and low voltage industrial robots are, as I said, a target application for GaN. And one of our key customers who's been successful using GaN for several years in this application is Ingenia, in this case, the Ingenia Everest, that uses the EPC 2022, which is pictured here. It's a 3.2 milliohm 100-volt device, and it's tiny. It's 13 square millimeters. And this allows a very, very small size motor drive that delivers very high efficiency. You can see a picture of the motor drive there on the next to the robot. And it's about 1 cubic inch, about an inch on each side. The value of eGaN devices for medical is huge. We have hundreds of applications in medical systems, and precision can literally save lives when used for surgical robots. Additionally, high frequency operation improves the accuracy and for diagnostics and display devices, which we're not talking about here, but GaN is just taking over in the medical field because of all the better things that it brings to medical devices. In drone applications, each arm of the drone has a motor, and a motor drive needs to be very small to be integrated with the motor in the arm. Industrial drones have an average of 6 motors per drone, and eGaN devices allow a smaller and lighter drone that have higher that have higher system efficiency and therefore a longer battery life, and they can fly farther. So it's really a no-brainer in the drone world to use GaN for those motor drives. By the way, these drones also use GaN for their LiDAR systems for collision avoidance, as well as for their charging systems to recharge their batteries. The e-mobility market for bikes and scooters is huge. There are 40 million units estimated to be sold in this year. However, it's not addressable. Most of it's not all addressable with GaN. eGaN devices are best when the solution is at the high end of the market and they need very small and very lightweight motor drives and very high efficiency in the systems. And so that's where we're seeing the GaN take off right now. DC servo drives are used for machine tools, packaging, textiles, manufacturing. In DC servo drives, the inverter is integrated into the motor, and therefore high precision and miniaturization is key. Additionally, high frequency operational that's achievable with eGaN devices reduces the EMI. And that reduces also a lot of equipment costs because these shielding and the cabling that has to be special for EMI shielding is no longer required. Now the sweet spot for eGaN devices is 10-volt DC to 150-volt DC and 1 to 2 kilowatt inputs. Outside this range, IGBT solutions are generally best. There are on average 10 electric motors per car for operations such as door locks, trunk latches, retracting roof, gas pumps, ventilation, battery management, seat controls, heating controls, electric steering, and that's just to name a few. Brushless DC motors are simpler to maintain. They're more durable, they're smaller, they're much more energy efficient, they're much quieter, they respond faster, and they're considerably lighter weight at higher operating speeds. So brushless DC motors they're also less prone to the types of failures that are experienced by brushless motors, and that leads to lower warranty costs. Now, cars are migrating to 48-volt bus architecture as our electric loads are getting larger and larger. And brushless DC motors become even more attractive for power levels between 30 watts and all the way up to a kilowatt compared with brushed or AC induction motors. So the value of eGaN devices in 48-volt automotive motors is that they can reduce the size and weight of the motors. They have almost no audible noise, much better torque, extended battery life, higher efficiency, and much more reliable. So now let's look at an application example using EPC's monolithic power stage integrated circuit. A practical high-performance BLDC motor drive requires the following functional elements. Voltage and current sense for each phase of the motor. The motor phase currents are measured using shunts where the voltage is amplified using a high-performance shunt amplifier. Voltage measurement is from each phase to ground using a simple voltage divider resistor network. Voltage sense for the DC motor supplied to the drive using the same techniques as for motor phase voltage measurement. There's also a housekeeping power supply for the power stage ICs that require 12 volts and a controller that requires 3.3 volts and an interface to the motor controller. An operational filter between the switch node and the motor connection can be configured either as harmonic or, let's see, where's that filter? There it is, as harmonic or an EMI filter. And a three-phase half-bridge power stage. You need that to do all the business. And each of the half-bridge power stages can use one of these EPC 2152 monolithic integrated circuits for, that are just an entirely monolithic power stage with level shifters, power FETs, drivers, and take a logic input. There they are. So we built one. We built the three-phase brushless DC motor drive. It was designed and built to operate from 15 volts to 60 volt DC supply and deliver a peak current of 15 amps into each phase of the motor. This drive can power a 400 watt NEMA 34 size brushless DC motor and measures just 55 by 45 millimeters, including the EMI filters. It includes the following features: a main DC supply, connection, and a housekeeping power supply that operates off the main supply to provide both the 12 volts for the e-power stage and the 3.3 volts for a controller. A motor connection, including a ground connection, a current sense for each of the phases, an optional filter to reduce DVDT on the motor windings, a heatsink mounting option, so you can put a heatsink on that and go even beyond the 15 amps per phase. Now we just zoomed in here, showing you the IC portion where the EPC 2152 power stage flip chip is mounted down onto the board. It can operate from 20 kilohertz through 1 megahertz. There you see the decoupling capacitors and gate drive support components. And finally, the controller and the connection to the controller there. So first, we tested the motor drive operating from a 48 volt DC supply, delivering up to 3.7 amps RMS into each phase of the motor with a field-oriented control sensorless algorithm. We used a 40 kilohertz PWM frequency. And in this case, we started off with a 500 nanosecond dead time. And that's typical of a MOS-based inverter. You need 500 nanosecond dead time because they have reverse recovery and they don't switch as fast. So this is what you get with a MOSFET. So in this case, we're using GaN devices to simulate a MOSFET. So using MOS, higher frequency results in higher losses because their switching speeds are lower. And dead time can't be further reduced because the MOS integral reverse rectifier that has to recover. So as you can see in these waveforms, the 500 nanosecond dead time is significantly distorting the phase current. Now let's crank it up. So we adjusted the dead time to 50 nanoseconds. Again, it's the same switching frequency, but all we did here was we adjusted the dead time. And that can only be achieved with gallium nitride. So we're still switching at 40 kilohertz, delivering 3.7 amps RMS into each phase of the motor, And look at how much smoother this waveform is with this 50 nanosecond dead time. We ran the inverter at 40 kilohertz to directly show the difference versus MOSFET-based inverters. And as a matter of fact, you can switch at much faster frequencies than MOS, which brings even more system benefits, such as, even smaller input filters and smaller entire system size. So, GaN devices can really go up to hundreds of kilohertz, which is rarely used in motors, but we're seeing more and more of it in some of these very high precision, very, very small motor drives. So let's look at a demo.
Here I want to show you a simple demo of motion control with the gallium nitride devices and gallium nitride IC EPC2152. This board here is the inverter, three-phase inverter based on EPC2152. The same board is there, and here you can see an adapter board for a microchip DSP and a programmer for the DSP controller from microchip. And here I have a servo motor connected to the EPC2152 demo board. So with gallium nitride and with a 50 nanosecond dead time, which is achievable only with gallium nitride, it's possible to get really silent operation. Now I changed the dead time of the modulation to be 50 nanosecond, which is achievable only with the gallium nitride devices, and I will show you the difference in terms of acoustical noise versus the 1 microsecond. So with gallium nitride and with a 50 nanosecond dead time, which is achievable only with gallium nitride, it's possible to get really silent operation.
Well, thank you, Marco. And now let's take a quick look at what EPC devices allow smaller, lighter, and more accurate motor drives like the one you just saw. So let's look at the discrete devices here. This is our 100-volt product portfolio from EPC. We have a full range of FETs ranging from 20 milliohms to 2.5 milliohms. Gate charge is very small, from 1.7 nanocoulombs to 11.8 nanocoulombs is the biggest device. And QGD is also very small, and that's really an indicator of switching losses. And in all GaN devices, QRR is exactly 0. It's ultra small, so you can see that ranges from about 1 millimeter squared to 7 millimeters squared, so it goes from teeny tiny to very small. And these are ball grid array or land grid array devices, and they can nest inside each other, so the same layout can accommodate different FETs to allow easy and flexible upgrades for efficiency and load current. So let's compare the EPC's eGaN FETs to major competitive motor drive MOSFETs in this case, and one can see that the EPC devices have the same on resistance as the other devices in about 1/5 the size, and they offer much lower QG and QGD, which are highlighted here. There's no reverse recovery loss, and at low PWM frequencies, they occupy about 30% of the total area versus a competitive benchmark. They don't have any reverse recovery. Enable minimum dead times, excuse me, which we saw makes a big difference in terms of acoustic noise as well as EMI. And at higher frequencies, so PWM frequencies, say 40 kilohertz to 100 kilohertz, these devices can further shrink the dimensions with our new Gen 5 devices overall. And, so in general, these EPC GaN devices enable miniaturization and just a whole lot more efficient, quieter operation. EPC also offers a flexible portfolio for motor drive applications. You can select, discrete devices on the left, integrated half bridges in the middle, or our new integrated power stage, which has the power. It has the half bridge with the power FETs, their drivers, level shifters, and takes it all the way to a logic level input. So we're introducing this 80 volt rated 10 milliohm EPC 2152-1 GaN e-power stage that really represents the next evolution of GaN FETs. And we think it really changes the way power conversion will be done in the future. This is a monolithic integration of power FETs in a complete gate bridge, such that you have logic in and you have power out. There are many benefits to this. It eliminates common source inductance, which is a major factor in overshoot and EMI generation, and also efficiency losses. The gate drivers that we built inside this IC are exactly matched to the FETs. And that allows us to optimize the switching speeds for reduced EMI generation, so we don't switch them too fast or too slow. Reduces voltage spikes and creates the shortest practical transition times in motor drive applications. It improves the thermal power distribution because the FETs and the switching circuit are all in one big thermal tub, so they balance each other thermally, and you actually get a net lower overall temperature. Let's see, there's better DVDT immunity. It simplifies PCB layout, reduces assembly component count. There's just so many things this thing saves, because a lot of people struggle with layouts with these ultra high speed, ultra tiny GaN devices. And this really takes away most of that struggle. This IC includes a 12 volt tolerant CMOS and TTL compatible input buffers, a logic interface with a power on reset, under voltage lockout functions, high voltage, high DVDT capable control signal level shifter, a synchronous bootstrap supply that gives you the proper high side voltage for the high side gate drive. And the whole thing is only 10 square millimeters, 3.9 by 2.6 millimeters. So this really does take away a lot of the design effort for both a motor drive and if you're doing any kind of a power converter that uses half bridges. So just in summary, EPC devices allow smaller, lighter, more accurate motor drives. And given the same on resistance, EPC eGaN devices are smaller than MOSFETs, have lower switching dissipation than MOSFETs, and have no reverse recovery compared to the aging silicon MOSFET. And the e-power stage digital in and power out family of integrated circuits further reduces size and design time and really simplifies the entire system. For more detailed information about our eGaN FETs and integrated circuits and motor drive applications, visit us at epc-co.com. And to purchase devices and demo boards, visit our friends at DigiKey.com. And with that, I'd like to open it up. What questions do we have?
All right, thank you, Alex. Now we're going to begin answering the questions submitted during today's presentation. As a reminder, you can still submit questions by typing your questions into the Q&A feature at the bottom of the screen. So let's see, Alex, our first question is, what's the typical DVDT applied to motor terminals? What's a typical DVDT applied at switching point in GaN-driven converters? And how will you compare DVDT applied to load with conventional silicon MOSFETs, which are comparatively slower devices than GaN?
Yeah, so that's a really good question. So if you have a very high DVDT in motor drives, you can have this problem of pinholing of the insulators. So you really want your DVDT to be moderated depending on the frequency that you're using. And that depends really a lot on what you're trying to achieve with your servo drive. So, we have servo drives that are operating at 100 kilohertz, even beyond that. And when you do that, you can use like 2 to 5 nanosecond rise times at 48 volts. So that's like 5 to 10 volts per nanosecond. And that doesn't have any impact on motor reliability. Now, with MOSFETs, you're operating it at 10 times longer rise and fall times. And therefore, there's much more switching losses, and that limits your frequency to well below 100 kilohertz.
Okay, next question. What frequency do you suggest for motor drive using GaN solutions?
So it really depends on your application. I think that many people in the MOSFET world with motor drives are running in the 20 kilohertz range, and that's really because of trying to get above the acoustic noise, the audible noise range, without having a lot of losses due to the MOSFETs and the reverse recovery and their slower switching speed. But with GaN devices, it's very easy to go to 40 kilohertz to 100 kilohertz, and you get much lower audible noise. You don't lose in efficiency, and your system shrinks because all your EMI filters get much smaller too. So 40 to 100 kilohertz is a good range for the applications we cited today in this webinar.
Okay, next question. What's the maximum value of DVDT before the filter?
Well, I think that as we said before, I think that you want to stay below about 10 volts per nanosecond before the filter. You want to avoid any of this pinholing. Marco, maybe you have something you want to add to that. You probably know a whole lot more than I do.
Yes, thank you, Alex. Just to give a clear point, usually with 10 volt per nanoseconds, which is quite common in the industry already with the MOSFET, even more 15 volt per nanosecond, we don't use filter at all. So the filter is really optional in our solution. It really depends on how big is the frequency that the customer wants to use. And so it is possible with GaN FET to achieve easily between 15 to 20 volt per nanosecond without filter, or going faster, definitely faster, and then using a filter to get a pure sinus. They're kind of a double-sided approach. It really depends on what the customer prefers for their solution.
Okay, next question. Can you touch on the robustness of the GaN-based motor drive, and what concerns are there regarding reverse conduction or avalanche?
So first of all, GaN devices are far more robust than silicon devices. And you can go to our website and look up our phase 11 reliability report. And it shows you in all dimensions, we fail our devices in all stress conditions to show exactly what they take when they fail. And from that, we built robustness models, lifetime models, and things like that. So to give you a very specific example, one thing in motor drives that can be important is the short circuit current. In electric steering, you have like curb lock and things like that that cause very high, very long duration short circuit currents. And we've tested our GaN devices, all of them, under short circuit. And you can see it on the reliability report. And with maximum gate voltage on it, the worst case scenario of unlimited current, the shortest time that any device failed was 9 microseconds. And the surface temperature of the GaN device, by the way, at that point was 1,000 degrees C. Now, just in comparison, MOSFETs are no longer semiconductors beyond 300 degrees C. So this is much more robust. Now, there was also a question of avalanche. And eGaN devices, or any GaN device, do not have an avalanche rating. And the reason is that, that the breakdown voltage of the GaN device is way, way higher than the rated voltage. So for example, a 100-volt device will have a breakdown voltage of 240 volts. And that has to do with some of the device physics involved in electron trapping. So in lieu of an avalanche rating, we give it an over voltage rating of 20%.
Okay. Next question, what are typical rise and fall times of GaN devices and the EPC 21521 specifically?
So the 2152's rise and fall time is actually tuned to about 1 to 2 nanoseconds. Now, discrete GaN devices, if you are if you want to go to the ultimate speed, we have demonstrated 140 picosecond switching speed on some of our devices. So you've got quite a bit of latitude there. But we've made the 2152s a more sedate 1 to 2 nanoseconds to virtually eliminate the overshoot inside the circuit.
Okay. Next question. Is there any advantage for a customer to design their own half-bridge circuit instead of buying the EPC 2152 for motor drive?
So the EPC 2152 is an 80-volt device that's made for about 12.5 amperes of output current. And it's a wonderful device. If you need more current, or if you need higher voltage, or you want lower voltage, you might want to go to either discrete devices from EPC or monolithic half bridges. But as time goes on, you will see from EPC, and I assume from our competitors as well, more and more of these monolithic half bridges. Because those of us who've been in power conversion a long time know that 80% of power conversion applications are half bridges. So you might as well glue them together onto one chip, which you can do easily with GaN, and take away all that other shrubbery and design time. So over time, it'll become more and more obvious you should just pick off the shelf a monolithic power stage.
All right. Next question. Can the EPC 21521 power stage be used in a boost configuration?
Yes. Yes, it can be used boost, buck. As a matter of fact, let's see, I think it's the EPC 9151 is a demo board that we have that has our GaN devices, the power stage integrated with its inductor and everything, and it can be either used as a boost or a buck, and it's actually a bidirectional 48 to 12 volt device.
Okay. Next question. We are seeing automotive applications for motor mount controls that are exposed to operating temperatures up to 140 degrees C. Do you offer any AEC-Q GaN FETs with operating junction temperatures up to 175 C?
Well, we offer a bunch of AEC Q101 eGaN devices that are used in cars today. They all are limited to 150 degrees C. So that is a limitation. We are thinking about coming out with devices at higher temperatures, but we don't have them right now available.
Okay. Let's see, next question. In order to improve the thermal behavior, the module can be connected to a heatsink through a TIM, thermal interface material. Do you recommend any software to carry out the thermal simulation of the module plus the heatsink? Yeah,
we use COMSOL, and I can get you more details if you send me your contact information. But we do a lot of simulations with COMSOL, and as with any thermal models, we also build the systems and confirm them physically. Which is, for anybody who's done thermal design, you know, it's extremely tricky to figure out what exact temperatures are actually going on underneath that heatsink. But we've done quite a bit of work to confirm our thermal models.
Okay. Let's see, next question. What is the effect of near zero common source inductance for this device? Could you explain more on dead time, why GaN have lower dead times?
Yes. So first of all, common source inductance, which is the inductance that is common to both the source and the gate, is the most egregious parasitic inductance in a fast switching circuit. And the reason is because the common source inductance develops a voltage that directly competes with the voltage on the gate. So it tends to slow down the device, and it also adds to ringing. So the elimination of common source inductance is a big factor in improving efficiency, lowering EMI, lowering all sorts of bad spikes through your system. Now, the question about lowering dead time with GaN devices, it comes from two things. One is GaN devices just switch blazing fast compared to MOSFETs, probably 10 or more times faster than a MOSFET. And the second thing is GaN devices have no reverse diode. They will conduct in the reverse direction, but it's actually because the FET turns back on. In a MOSFET, silicon MOSFET, a diode turns on in the reverse direction. And that diode needs time to recover. And that's this reverse recovery charge, which can be tens of nanoseconds in a MOSFET. And also is temperature dependent. It gets longer at higher temperatures. It's current dependent. It gets more at higher currents. So this reverse recovery is a major factor in generating EMI, in slowing down your circuit, so you have to have a longer dead time, and also increasing your losses because you're sitting there, kind of waiting for this diode to stop dissipating for a long time.
Okay. Next question. How is the price comparison of GaN MOSFETs with respect to the same voltage rating and same RDS on for silicon MOSFETs?
Great question. We've been showing for about 3 years that we've priced our latest generation MOSFETs, the generation 5s, which we showed you earlier, right in the middle of the pack of the most common MOSFETs at high volume. So that is true for 100 volt. It's true for 200 volt devices. And that's for the same voltage and same on resistance. So you basically get all this extra performance and all this size advantage for free.
Okay. Let's see, next question. Why is GaN good for low inductance motors? For example, the slotless BLDC motor that you mentioned.
So when you go to low inductance motors, you have an opportunity to go to much higher frequencies. And these low inductance motors can generate enormous torque density, the density of the system compared to the amount of torque it produces. Enormous advantages there, but you have to go to higher frequencies. So we see these very low inductance motors running at 250 kilohertz. Now that would be just unthinkable for a MOSFET. It just couldn't do it. But with GaN, it's no problem. So this new generation of motors, these slotless motors, I think it'll be a very important factor in some of these systems that are very sensitive to size and efficiency and weight.
Okay, let's see, next question. Would you suggest to operate the half bridges of a motor drive with eGaN under soft switching conditions?
Yeah, Marco, what do you think?
I think, that hard switching, it was done for hard switching. If you're going soft switching, you're just reducing the dissipation, the power dissipation. So I don't see problem with it. The most important thing is always doing complementary driving and reducing the dead time always to the minimum. And then that's no problem at all.
Yeah, sometimes people are using soft switching to save on switching losses. That's not going to be important in GaN devices at these frequencies because the switching losses will be negligible. And some people, use the resonance, for other reasons, including lower noise. But that really won't be an effect here. So you can go resonant. It doesn't hurt anything. I don't think it helps much. And Marco, am I right about that?
Yeah, exactly. That's what I was saying. So it's not forbidden but maybe there's not big advantage on doing it.
Yeah, as opposed to with a MOSFET where there is an advantage.
Okay, thank you. Let's see, the next question, is the motor power board available for sale to customer doing motor control evaluation?
Yes. Yes. Let's see, Marco, what's the part number on that?
In the motor board, the evaluation board is EPC 9146. It's under characterization right now and will be released soon to the public. And each of this board comes with an adapter board that is done for the most common motor control development kit by major vendors. So that's really you plug the boards together, similar to the video that I've shown. And so then you can easily reuse your existing motor control development kit from your preferred vendor.
Yeah, so there's a picture, and I know it's being released this quarter, isn't that right, Marco?
Right.
Yeah. So, and then there are all these controller cards. The one that I'm showing here is using the microchip controller that was used in the demo. But we also have plans, I believe, for TI and ST and Renesas plug-in controller boards that'll be introduced either simultaneously or shortly after the boards are introduced.
But moreover, what we're trying to do, we want to make our power board to be compatible with the original development kit from the vendors, so that we can simply, if a customer is already owning a development kit from a vendor, let's say, for instance, the DSP microchip development kit, then can simply connect our board to their to the development kit from microchip without doing anything, because we just gave also the adapter board.
Yeah, and here's the adapter board all the way to the left.
Okay, next question. GaN FETs have a high switching speed, which concerns me about capacitance in the wires going from the control board to the motor, and motor capacitance causing large current spikes. I could slow down the GaN FETs, but wouldn't that reduce efficiency?
Marco, why don't you take that one?
Yeah, obviously, if you reduce the speed of switching, then you are impacting a little bit on the efficiency. That's true, but the figure of merit in that case is always better than if compared to MOSFET. And also, it's really important the way the layout is done, so that all the capacitive coupling, especially with the motor cables, which is there, it's the spikes of the current are reduced as much as is possible. So you have to find the right compromise without being too much penalized because of power dissipation during the switching event. So at the end of the day, it's always an advantage going with GaN.
Yeah, and I think that a good way to slow down these DIDT transients is to put a little inductive element near the eGaN FETs in series with the switch node, something like a ferrite bead, which can slow down this leading edge current spike. It doesn't affect the switching speed of the device. Let's see, I think we may have an example of that somewhere here.
If you keep in the picture there, there are the two ferrite beads that are just there in the optional filter. The two black spots on each of the face. These are the ferrite beads. They are surface mount devices that can be used and put simply in series with the phase of the motor, and this will reduce the capacitive current between phase to phase. But yeah, one thing, it's really not mandatory. That's the point.
Okay. Next question. Let's see. Are there any applications where soft switching is combined with paralleling for highly efficient applications in your portfolio?
We have lots of application notes written about that, and I would like to say that GaN devices parallel really well, you know, with MOSFETs, particularly low voltage MOSFETs, they have a problem. It's called a Spirito effect, where if you're not careful in paralleling, they will go into a thermal runaway. One device will start hogging current, and it will cause it to hog more current. It'll go into a loop and blow up. So GaN devices parallel much better than MOSFETs. And so it's also easy because there's low gate charge, and there's also gate threshold stability over temperature. MOSFETs will tend to, the threshold will tend to be cut in half between room temperature and 150 C. GaN devices, it's less than 10% shift. So you can really do a very simple drive that runs many GaN devices in parallel. We have an application note. Just go on our website and type into the search paralleling, and you'll come up with it. But it is an added benefit of our GaN devices over a MOSFET.
Okay, let's see. So we've got a few more minutes. Any more last call for questions for Alex and Marco? Let's see. Okay, here's another one. Is there a thermal solution that lets me eliminate the insulated metal substrate from my design?
So let me go to the thermal slide here for a second. The answer is, so here's the thermal slide. One thing that we found extremely useful are these thermal shims, which I think that you can see here. I'm even going to make a crude attempt at drawing around it here, so you can see this shim right here. It's actually a surface mount component that you can buy in different standoff distances and surface mount right onto your PC board. And then you clamp your heat sink onto it, and it sets the distance between the bottom of the heat sink and the top of the FET. So it sets this distance very precisely. And then you can either use thermal insulating material, or you can use thermal gels, these so-called gap fillers. And in this simulation, and actually in the real world, we use 6 watt per meter Kelvin gap filler, but you can get 10 watt per meter Kelvin gap filler as well. I think T Global sells that. And so you don't need a thermal insulating material. You just squirt a bit of goo in there and squeeze it all down, and you get an even better result, because the thermal insulating material can get all 6 sides of the FET and cool it down better than the thermal insulating material. You know, these little sheets of TIMs.
Okay, next question. What's the short circuit capability of GaN? So for how much time half-bridge can withstand short circuit?
As I mentioned earlier, we take our device to destruction in every dimension, every stress condition, mechanical, thermal, short circuit. And we have this marvelous discussion of that in our phase 11 report, where we show that if you apply a 5-volt gate signal on our device, which is what most people do, and then you subject it to a short circuit condition, you'll tend to get kilowatts of power running through even the tiniest device. Matter of fact, our smallest device will absorb 3.6 kilowatts of power for 13 microseconds or longer. That was the minimum, 13 microseconds before failing. So that gives you plenty of time to detect and clamp that circuit. So there's very good short circuit capability in these parts.
Okay, next question. Would this sort of technology have any benefit to driving stepper motors, more efficient or less ringing resonance?
Marco, what do you think?
Yeah, may I take this question? So in stepper motors, especially when doing microstepping, one common problem, pitfall from the MOSFET is that since the switching is not really accurate and precise, to have the right microstepping, it is important to decrease the frequency. That's not the case for gallium nitride, because you have very sharp and precise and accurate switching that should really help in doing the micro-stepping in stepper motors. So having at the same frequency, having better accuracy in positioning. So that's for sure because of the very sharp way the rise and the fall of the GaN FET.
Okay, let's see here. Next question. Can you comment on what % of GaN sales will be generated from motor-related applications in 3 years?
So, you know, GaN is really right now very rapidly growing in, you know, automotive applications, primarily, you know, DC to DC and LiDAR applications. But motors are going to come up fast for automotive world, which means about 2024 and 2025. In the commercial world, we're already seeing quite a bit of applications in these, I'll say, robotic and drone applications. So today, with, you know, DC to DC being the biggest market for GaN devices, and the second biggest market being lighting, particularly LiDAR applications, motor drives would probably be number 3 or so. And I would expect it to be, much like in the world of MOSFETs, maybe a 10 to 20% of the market. I would also like to point out that another big market, which we didn't even discuss, is space market, where there are lots of motor drives, and we have lots of products in these drives that drive the inertial systems that keep the satellites stable, and as well as robotic missions to other planets.
Okay, well, thank you guys. So thank you, Alex. Let's see, and thank you, Marco. And thanks to everyone for attending today's webinar. If we didn't have a chance to answer your questions, we will reach out to you with a response. Likewise, if there are any additional questions, please send them into info@epc-co.com. Once you leave today's webinar, you will receive a survey on the presentation, and we would appreciate if you would complete that and provide your feedback. You will also receive a follow-up email 24 to 48 hours with a link to view a recording of today's webinar. Thank you for joining us today, and we hope to see you again at the next webinar. Visit epc-co.com for information, and have a great rest of your day.
Thank you. Thank you, David.
Thank you. Thank you.